Okay, product and quotient rules and higher order derivatives. So these are the objective in this section. We are going to talk about product rule, quotient rule, and we're going to talk about some of the derivative for the trigonometric function, the leftover trigonometric function from previous section, and then higher order derivative. So what is product rule? So whenever we need to find the derivative of product of two different functions like this, the product of two differentiable function, keep in mind both of them should be differentiable. You should be able to find the derivative individually, otherwise this rule doesn't work. Then if they come as in product, then you can use this rule. So what is the derivative of the product? The derivative of just copy the first function times it by the derivative of the second function plus leave the first function, second function now, and then find the derivative of the first function. So, let's say you have these two functions. For example, this is your function f of x, and this is your function g of x. Now, for finding the derivative of this product, you need to find the derivative of the first function, which is use the power rule. The derivative of 3x is 3 minus the derivative of 2 times x squared is 2 times x to the power 1, because the derivative of x squared is 2 times x. So this is 3 minus 4x. The derivative of the second function is, the derivative of 5 is 0. The derivative of 4 times x is 4. So now go back here and then just plug the value for the f, g prime, z, and f prime. That's how you can find the derivative of h of x. So this is the first function times the derivative of the second function plus the derivative of the first function times the second function. Just plug this value back here. What is f of x? 3x minus 2x squared. What is g prime of x? 4. What is f prime of x? 3 minus 4x. What is g of x? 5 plus 4x. And that's how we can find the derivative of this product function. So this is the complete work here. And eventually, after finding the derivative, putting the value, you have to simplify things. And after simplification, you are going to get this value here. Okay? That's the product rule. The quotient rule, whenever you have something, like this, a function on the top and another function on the bottom, and the derivative of both of these functions are possible, both of them are differentiable, the quotient f over z, this is the division sign, of two differentiable functions f and g is itself differentiable at all values of x, for which, keep in mind, the function on the bottom should not be 0. Moreover, the derivative of f over z is given by the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. Meaning, look at here. This is the denominator function times the derivative of the numerator function minus this is the numerator function times the derivative of the denominator function divided by the square of the denominator function. It's not derivative, it's a square of the derivative. It's a square of the function. Okay, so that's called quotient rule. This product rule and quotient rule are very, very important rules. So just write it down a couple of times, so that you can remember this formula. Okay, find the derivative using the quotient rule here. As we know, the quotient rule here, if you have a function on the top and function on the bottom, this is the quotient rule. So let's assume that the top one is f of x and then bottom one is g of x. So to use the quotient rule, you have to find f prime, which is the derivative of the function on the top, which is 5 times the derivative of x is 1 minus the derivative of 2 is 0, so it's a 5. G prime is the derivative on the bottom, which is 2x for the first one and 0 for the second one. So these are the derivative. So if you want to find out the derivative dy over dx using the quotient rule, it's supposed to be f prime times g minus f times g prime divided by g square. Okay, plug the value. F prime is 5, g is x squared plus 1, and then minus f is 5x minus 2, and then g prime is 2x, and divided by g square, which is the square of the function we have given on the denominator. So after this, we just need to distribute and do the simplification, and this is the work, complete work here, and just do the distribution, and then just do the simplification. That's your final answer. Derivative of trigonometric function. In previous section, we discussed about derivative of sine function and quotient function. Derivative of sine function is, it's a cosine, and derivative of quotient function is, it's a negative of sine. Now we try to, use some more derivative for trigonometric function. The derivative of tangent is secant square x. Derivative of secant x is secant x times tan x. Derivative of cotangent is negative of quotient square x. Derivative of cosine x is negative of cosine x times cotangent x. So you have to know all this derivative formula, and then if you go further and try to do some examples, this is the function we have given. For finding the derivative of this function, you need to find the derivative of the first function, which is 1, and the derivative of second function. From this formula, we can say it's a secant square x. Here, it's a product of x times secant x. So this is one function, and this is another function. So you need to use product rule. So the product rule is find the derivative of the first function times by the second function plus find the derivative of second function times it by the first function. Okay, so first function times it by the derivative of the second function plus this is derivative of, what is that? This is derivative, this is second function, and then this is the derivative of the first function. Okay, so you can write this thing first, and then after that this thing. It doesn't matter, plus sign, back and forth, just use the product rule. Okay, so now let's go further. Higher order derivative. Sometime we need to find derivative of derivative, like situation like this. Look at here. A velocity function is found by differentiating a position function. But if you find the derivative of the velocity, it will give you acceleration. So acceleration function is found by differentiating a velocity function. So it's a higher order derivative of position function. So this is your position function. If you find the derivative first time, that's the velocity. If you find the derivative second time, that's the acceleration. So higher order derivative could have some meaning. We might have to find the higher order derivative. Okay. These are the notation we use for the higher order derivative. For example, this is the first time. 1 prime means one time derivative. Double prime means 2 times. 3, third time, fourth time, and keep going like that. Or maybe you can use this notation as a function notation, or maybe like this, dy over dx form. So these are the different type of notation only for finding the higher order derivative. So let's look at one example here. Because the moon has no atmosphere, a falling object on the moon encounters no air resistance. In 1971, astronaut David Scott demonstrated that a feather and a hammer fall at the same rate on the moon. The position function for each of these falling objects. This is the position function. This is the graph of the position function, where s of t represents the height in meters and t represents the time in seconds. Now the question is, what's the derivative of this position function? Can you find it? Yes, of course. It's just a simple derivative. Find the derivative of the first part. It's a negative 0.81 times 2t plus derivative of 2 is 0. So there is no plus. Can you find the second derivative? Yes, of course. The derivative of 2t is 2. So it's a negative 0.81 times 2. Can you find the derivative of this one? Yes, but this is a constant function. That's why the derivative of this function would be 0. And then no matter how many times you find the derivative after that, that would be 0. So that would be meaningless. But the good thing about this example here is this is the position function. The first derivative is the velocity. The second derivative is your acceleration. So position function, velocity, and acceleration. Now the question here, if you read the question here, what is the ratio of Earth's gravitational force to the moon's? Remember, there is a standard value for the Earth's gravitational force, which is 9.8. And acceleration is also called gravitational force, acceleration due to gravity. This is the moon's acceleration we found. So to answer this question, you just have to divide 9.8 by 1.62. And eventually, by dividing that, it gives you 6.0, which is the ratio you have. Earth's gravitational force to the moon's gravitational force is approximately 6 times. Okay? So that's how we can use the higher order derivative.